Okay, I opened a minute late, so I'm gonna get going. So I'll give a few minutes before Trevor gets going to let everybody get settled, but I think our attendees have sort of leveled off now. So hello and welcome to today's webinar, Leveraging Information from Climate Scenarios for Robust Infrastructure Planning. This webinar today is part of the PIEVC webinar series on climate change vulnerability and risk assessments for infrastructure. And it is one of the many knowledge building activities offered through the PIEVC Practitioners Network. The network itself is an online platform that facilitates engagement and collaboration among PIEVC users, as well as infrastructure owners and operators, both internationally and within Canada. The network is free and open to anyone who is working to enhance the resiliency of infrastructure to the impacts of climate change. And just after I finish speaking and turn it over to Trevor, I'll put a link in the chat for those of you interested in joining. I recommend you join so that you can be made aware of these great events in the future. My name is Claire Sanders. I'm the Manager of Engagement and Communications at the Climate Risk Institute, and I'm pleased to be moderating the webinar today. I would like to acknowledge that I'm hosting this webinar on the traditional territory of the Three Fires Confederacy of First Nations, which includes the Ojibwa, the Odawa, and the Potawatomi. Indigenous peoples have long modeled sustainable land stewardship practices. And at the Climate Risk Institute, we're continually trying to improve our knowledge, processes, and relationships so that we can highlight and integrate Indigenous perspectives and knowledge of climate change into our work. I invite you all to introduce yourselves and share the territories you're joining us from in the chat if you would like. If at any time you run into issues or you have a question about using Zoom features, you can open the chat box and locate my name or host and panelists on the list and send me a private message. Your microphones have been automatically muted to avoid any audio distractions or feedback during the webinar. And we're also recording this webinar today, and we'll send a link out to everybody registered as well as the slides and put them in the Practitioners Network as well. There is a dedicated session at the end of the webinar for discussion, but that doesn't mean you have to hold your questions until then. Feel free to put your questions into the Q&A box. It's open now. The chat box is also available if you would like to submit comments, but it's much easier to keep things organized and make sure we don't overlook your question if it's in the Q&A box. You will also be able to raise your hand and ask questions verbally as well. So you raise your hand and I can go and unmute you, and we would certainly welcome. And I think in some ways, certainly this complex discussion and topic today may be better addressed through verbal questions and discussion. So don't hesitate to put up hands and ask verbally as well. Kerry Pomeroy is on the back end with me here today as well to help manage some of those questions. So he may respond either in writing in the chat box or in the chat or in the Q&A box, and may interrupt Trevor from time to time with questions, clarifying questions. If there are any questions we can't get to at the end, don't hesitate to go over to the Practitioners Network. We will try to answer them over there in the coming days for sure. So with that, I'm really pleased to be able to introduce today's speaker, Trevor Murdock. He is the Manager of Data and Products at the Canadian Centre for Climate Services at Environment and Climate Change Canada. Trevor has been a climate scientist since before it was cool, thanks to a master's degree in paleoclimate modeling from the University of Victoria in 1995. Trevor focuses on helping people do useful things with localized climate projections since the inception of the Pacific Climate Impacts Consortium, or PCIC, in 2005, and the Canadian Institute for Climate Studies before that. It was my personal pleasure to meet Trevor at the PIEVC Global Forum in Vancouver in April and wander the streets with him on the Green Infrastructure Tour. So I'm really, really pleased he can join us today. Thanks so much, Trevor, for being here. And I'm going to turn it over to you.
Thank you very much, Claire. And I also want to acknowledge where I'm joining from is the territories of the Lekwungen speaking peoples, and acknowledge with respect that the relationships of the Songhees, Esquimalt, and Wasanich peoples with this land and waters and laws and languages continue to this day. in terms of the presentation, so we've got a title here of leveraging information from climate scenarios for robust infrastructure planning, which is a fancy way of saying which scenario should I pick. You'll see this on this link here to PIEVC.com/CCCS. If you're in front of a computer, you can go to that link because we'll be using some interactive polling during the webinar. You can also join in on the interactive polling just by sending a text to 37607. So that's the phone number, even though it's only 5 digits, that's the phone number you'd be texting. And just send the letters CCCS to that number, and then you'll get an invitation to participate in the polling. You'll see these instructions should be on all of the polling slides as well. So just in terms of what we're going to be covering, we'll do a little bit of review just to make sure we're on the same page about what we're talking about, the role of scenarios in risk assessment. Since we're at the PIEVC Practitioners Network webinar, I assume folks are familiar with risk assessment. We'll do a little bit of review of these 2 Learning Zone articles that were in the event invite, Understanding SSPs and Uncertainty in Climate Projections. And I will note that because this is kind of like a second level discussion, included in the slides, I'm not going to go through all of these, but included in the slides that you'll get afterwards will be a whole bunch of other resources. If this conversation lands kind of feels like I'm assuming that you already know some things, you want to sort of go back to basics, there'll be a lot of useful resources for that in the slides that you receive. And we will have the time for discussion. And as Claire mentioned, we have the Q&A as well. And I do want to admit the presentation is all in English, mais vous pouvez poser vos questions dans la langue de votre choix et essayons de répondre en français dans le chat ou après par courriel. Okay, so let's dive right in. Oh, I was going to mention, we'll touch on what about global warming because they're related. So just to kind of test out the polling, I have this question about where do you usually get climate data from for risk assessments? And so the first option being one of the national data portals like climatedata.ca or Climate Atlas, from one of the regional portals like Plan to Adapt or Portrait Climatique. There are others. Directly from a climate service provider like PIEVC, Uranos, Climate West, Climatlantique, from a consultant. And many of these options have here, or if you just want to add to this, feel free to comment in the chat with comments on this. Or if you have interesting thing to mention about where you get data, that could be part of the discussion as well. Mostly, I just wanted to get people familiar with the polling function here. And so it looks like mostly national data portals, but the regional ones serving an important role as well. And yeah, both direct from the climate service provider and from consultants. Okay, cool. So you can keep answering. If you haven't had a chance to answer this, I'm going to go on to the next slides, but this poll will stay open until we get to the next poll. And I've spaced them fairly far apart, so you can go ahead and answer. I'll give you one more second to memorize the letter. I think you can answer multiple on this one as well. So okay, all right. So just to make sure we're on the same page of what we're doing here, what this talk is about. So everyone, I'll assume, is familiar with this sort of PIEVC matrix. This is true of any risk assessment. We're effectively multiplying some kind of numerical quantitative ranking of consequence with some numerical ranking of probability of occurrence. And so if we have some past event, such as a flood, or this could be extreme heat or whatever, what climate change will do is generally it'll move it to the right. I should point out, in some cases, especially things like extreme cold, but even in flooding, in some cases, climate change may move things to the left or temporarily to the left. But for most things, we're talking about increased risk. And so what we're talking about, what this webinar is going to focus on is when you have your event of interest, you know your consequence, going from knowing what the probability of occurrence is today to what will the probability of occurrence be at some future time under climate change, how do you choose which scenarios to use? And we're really going to focus on more the scenarios in particular, not just where do you get your data and all of that other stuff, which is all kind of wrapped up in it as well. But so we're going to dive kind of deep on the scenarios bit, and then of course the purpose of PIEVC is so you can identify these things and bring the consequence down. But we're gonna go in on that top area. So I'll start by reviewing. This is the Learning Zone article that was linked in the chat. I'm going to include a couple of slides and then just sort of run through the takeaways. And so this is future projections for Canada as a whole, with following 3 of the SSPs. These are the newest, the shared socioeconomic pathways, and the highest one that we have available to us is SSP 5 8.5. And this is the high fossil fuel development throughout high fossil fuel development world throughout the 21st century. So, and then contrasted with the one in the bottom there is SSP 1 2.6 is consumption oriented towards low material growth, lower resource and lower energy intensity. And there's, this one is to achieve this one, we need to get to net zero emissions in a decade or 2. And we need to stay constant at net zero. So any greenhouse gases we continue to use, we need to be putting into the ground, keeping in the ground an equivalent amount of CO2 and other greenhouse gases. So there's a big range between those. There's a little bit of debate around, is the top one even plausible? Is there enough coal in the world to get to that one? And similarly at the bottom, is this even plausible? Do we have the appetite globally to meet that level? But the point that I want to start with is that what differentiates these is it's the socioeconomic assumptions behind what we do as humans. So that's what differentiates them from each other. And you can learn more about that at the Learning Zone article. But in terms of, okay, so that arrow, in the PIEVC process of putting the probability over to the right, how far does it get? What are the implications for that? And for 8.5, what I want to point out is that by the end of the century, we're just looking at temperature here, but it's sort of true of other impacts as well, major change by the end of the century. So there's a big difference between 8.5 and the others. I skipped over 4.5, but the socioeconomic assumptions are in between the 8.5 and 2.6. So there's a big difference in terms of impact by the end of the century. But if we look at the middle of the century, these two are pretty close to each other. And then this is if we manage to get to net zero in a decade or 2 and stay there, maybe we over-design if we look at this area, but that's a good problem to have in a sense. So, but the similarity of the other 2 scenarios by the middle of the century, you can actually translate that as well into this level of warming under 8.5 by the middle of the century does actually come to pass under 4.5 as well. It's just that it happens maybe a decade or 2 later. And the other important point to make on this is that all of these scenarios, even if you want to be very optimistic, opposite of engineering conservative, just you have utmost faith in our technology and policies to get us to very low greenhouse gas concentration. Even if you plan for this, that's going to be a lot better. You're going to reduce risk considerably, maybe not ideally, but considerably compared to just using the pass only. So no matter what we choose in here, we're doing something better than using historical data only. The other last thing to say before I sort of summarize what to know about SSPs, and then I'll maybe take a breather and see if Carrie has any questions in the Q&A to bring to light before going on. The last point I want to make here is just to show how far there's a little more. If you peel back the layers of the onion in SSPs, there's a lot that goes into it. So, at a high level, I kind of characterize the difference between this SSP 5 as fossil fuel development and the SSP 1 2.6 as a very sustainable path that gets us to very low greenhouse gas concentration. And what differentiates them is these socioeconomic assumptions. But when you're trying to plan when you're designing scenarios that depend on such a large number of things, everything from economic growth, interregional cooperation, technological advances, population growth. There's a lot of assumptions that go into these. You have sort of a lot of knobs to turn, but you have to explore all of the possible futures that can occur. And so even under these 5 different sort of narrative storylines, I didn't talk about them all, but sort of contrasted the 2 most different from each other. Under all of these 5 storylines, there's actually a whole bunch of these black lines represent a bunch of plausible different scenarios that can happen. And so the reason we have these 3, and there's actually more than 3, which we'll touch on the next slide, we tend to focus on a small number of them. They're called marker scenarios. Those are the ones we spend most of the time planning for. It's not because there's anything particularly magical about those ones. They're not like the most likely paths to be followed or anything. They're picked purposely because they span the range. And so each one of these has a wider range than is represented by that one. And we sort of pick some individual ones. And you can see here, if you look closely, SSP1, for example, actually has 2 different sort of landing points in terms of the number at the end. And that number, the higher that number is, the higher the concentration of greenhouse gases in the atmosphere, the more warming we have. Okay, so I'm going to try to summarize all of that and add a couple other things.
Just before you go ahead.
Sure. Yeah.
There was a question in the chat that I feel as though you could answer to add some value here. Is just what the numbers mean. And
the numbers. Okay, that's great. That is great. Thank you for doing the ghost voice on that one. I almost mentioned this anyways. It's actually kind of a cool thing. So the numbers here, the 8.5, if you had an 8.5 watt light bulb at every square meter of the top of the atmosphere, and you had it turned on 24/7, the amount of energy that those bulbs would emit is equivalent to the extra energy that is trapped by the greenhouse gases. So that's why the higher the number, it's the higher the additional forcing of the atmosphere. If that makes sense. So those numbers are actually, there are units associated with them. Don't refer to them, but it's the SSP5 8.5. It's 8.5 watts per square meter. Forcing at the top of the atmosphere, 1.9 watts per square meter. So you can actually, when you're comparing 8.5 and 4.5, it is about twice as much forcing because that number is about twice as big. But it's referring to at 2100, so it's watts per square meter at 2100. You might regret of asking after hearing that nerdy answer, but I think that's super cool. Okay, so what to know about SSPs? The first thing is that they represent fundamentally different socioeconomic assumptions. So I think I showed that. They map out the range of plausible future conditions. Again, there may be some debate about both the top and bottom, but they're really intended to map out what could happen. What thing to point out, so I'm talking all about SSPs here. We still have the RCPs that were associated with the previous assessments, and the details are a little different between the SSPs and the RCPs, but they land at the same levels. And so what I mean by that, just one example, if you care about ocean acidification, for example, and you look at SSP 8.5, which is associated with the most recent assessment report, and compare it to RCP 8.5, you actually find the ocean acidification is a little different in those two because we've learned more about in terms of what we expect greenhouse gas emissions to be, and the relative amount of CO2 versus methane is different in those two scenarios, even though they add up to the same amount of watts per square meter at the end of the century. And ocean acidification only cares about CO2. It's essentially ocean acidification is like adding carbon dioxide to your pop. It's making the ocean into soda water, and so methane doesn't affect that. So with some minor details like that, even though there are differences in the scenarios, the numbers are the same because they add up to the same amount. It's the same amount of light bulbs at the top of the atmosphere. The other point is that there are some additional levels that are available in the SSPs that we didn't have with the RCPs. So notably 2 at the bottom, not super relevant for risk assessment because, as I mentioned, the 2.6 already is the opposite of engineering conservative. You got to be pretty optimistic to hit that 2.6, and these 2 just straddle the 2.6, one less, one a little more. This one, 7.0, is one that I expect, they're not readily available now, but I expect that in the coming years, we will likely have climate projections for this additional scenario 7.0. Right now, there's not really anything readily available between 4.5 and 8.5, and there's a lot of space in between there. So we might have 7.0 come along. And yeah, so the last point I want to make is that and this is made in the article, that for any new analysis, you want to use the SSPs, and those are associated with using the latest data, which comes from CNIP 6, associated with the 6th assessment report of IPCC. But any analysis that has used the RCPs is still valid. If you're embarking in a new analysis, you might as well use the most recent projections. But again, it's only the details are going to be different between the 2. The overall magnitude of findings are going to be pretty similar between them. So I wouldn't throw out any work that has used the RCPs. And so on that, I want to have a popularity contest. So far, based on what you've heard so far and your previous knowledge, which scenario is the best for risk assessment? And if I set this up right, you should only be able to choose one answer here. And while folks are thinking about this, I'm going to catch up on the chat. Okay, great. And again, I'll give maybe a 30-second warning. If you're having technical difficulties entering your number, just make a note of the letter that's associated with the choice you want to make, because this will stay open again until I get to the next poll, and I've spaced them. I think I've spaced them fairly far apart. Yes. So that'll stay open, and it looks like we have a pretty big consensus for SSP 5.8.5, followed by RCP 8.5, and then, okay, a lot of interest in SSP 3 7.0. Interesting. Good that we're thinking about working on that one. All right. So the other Learning Zone article is on uncertainty in climate projections. And I'm going to pull out a figure that's from the paper that's linked there, intentionally not fully labeled here. And so this won't be a poll EV question, but I just want you to think to yourself. So one of these is precipitation, one of these is temperature, and just think in your mind, decide which one you think is precip and temperature. So I'm going to describe the colors here, what we're looking at, and then see if you can guess which one is precip or temperature. You can put it in the chat, but in a minute, give people a chance to think for themselves. So, okay, so the orange color on these charts we're looking at through time along the horizontal axis, and we're looking at how much. Okay, so something I meant to mention this when I'm actually going to zoom back to it. Oh, no, I'm not, because it's going to mess up the polls. So when we looked at those, the RCPs for Canada, there was, and I contrasted the SSP 5.8.5 with 2.6. Within those curves, there was a range. I would have these solid lines, horizontal lines going through the middle, but around them, there was a range. And so that range of future projections is made up of 3 different sources of uncertainty, categories of uncertainty. The orange one is internal variability. We'll say more about this in a moment, but that's essentially natural variability. That's are we in an El Nino year or a La Nina year? What phase of the Pacific Decadal Oscillation are we in? The green is the one we're focused on today, scenario. Which scenario do we choose? And so what this is showing is how much of the range in the future projections is determined by choice of scenario. And then blue is climate model uncertainty. Climate models are imperfect. And so how much of the range just comes from climate models disagreeing with each other. And so there's not too much we can do about the climate model uncertainty. It grows with time, especially for this variable. The scenario uncertainty, so I'm going to sort of remake the points that I made in terms of SSPs, but looking at it in a different way in terms of like how much does it actually matter. So for this variable, for the middle of the century, it almost doesn't matter. This choice of scenario has almost no effect. It's dominated by natural variability, the range. And for this variable, are folks ready? I'm just going to come out and set. So this is precipitation on the left and temperature on the right. So for precipitation, because it's such a noisy variable, the difference between a dry year, we're looking at Western Canada. So, and this is winter precipitation. So the difference between a wet winter and a dry winter in Western Canada, this is the prairies, is so large that even though there is a precipitation climate change signal here, and it's an increased precipitation in winter, and that signal is important when you come to look at risks. Even a 10% increase in winter precipitation can be associated with a much larger increase in extreme events and therefore flooding, and the stuff that we care about in risk assessments. So it's not to say that the climate change is small, but what this green is saying is that the interannual variability, so the natural variability, is so large that the choice of scenario has very little impact on the future projection that we're looking at. Towards the end of the century, it still explains about 10% of the variance by the end of the century. So it's something. It's not negligible, but it's still even small then. And if we go over to temperature, in this part of the world, the variance explained by temperature in the middle of the century is kind of similar to precip in the end of the century, so about 10%. And by the end of the century, as we saw before, now your choice of scenario is comparable. It's almost as big as the interannual variability. So it's massive. So the point here, though, is that how much your choice of scenario matters will depend on three things: the location. So this happens to be for Western Canada. It'll be different in different places. It depends on the time you care about, if it's the middle of the century or the end of the century. And it depends on the variable. So here we're just looking at winter temperature and precipitation. It'll matter more for some variables than others. And so just to sort of put that together and summarize the uncertainty article, these three sources of uncertainty, there's not a lot we can do about any of them. But the natural variability in particular, this is the one where this is an irreducible component of the climate system. It's a range that we should explicitly consider. So in an ideal world, you think about the top end of that range. It is present in historical observations, though we haven't always considered it explicitly. It's kind of baked into some of the things we looked at, so that we often look at in risk assessment. So, some of the indices like return periods. The reason we're interested in a 1 in 20 year event is because that's the one of the things that goes into the statistics of those extreme events is it a wet year or a hot year or whatever. Okay, so scenarios uncertainty is the one we're focused on here, and this is the part that depends on human behavior, policy, technology, all these assumptions. So it's really hard to rule out that full range with any confidence. And the top and bottom may be a little outside of the range of most likely, but that's sort of with design. That's in risk assessment. You don't want to restrict yourself to only the things that will definitely happen. That's sort of the whole point. Is you're doing a bit of a what if exercise. So you want to consider a high end and a low end to explore the range of possibilities. And the model uncertainty is actually relatively small in this. And it is something that's generally sort of improving. And I do want to point out, when I say model uncertainty, we're talking about everything in the chain. If you're using statistically downscaled climate projections, then the downscaling method itself and the historical observations that are used by that statistical downscaling are also part of that batch of uncertainty. And so, but a good chunk of the range, even at the end of the century, even for winter temperature that we just looked at, you still, a lot of it is just that interannual variability, that natural variability. That's not going away. Okay, so returning back to this, why what we're here for. This getting at the scenarios that underlie this choice. What do we actually do when we in risk assessments when we come to assigning these probability scores? So I want to go a little bit deep on this before I finally get to trying to answer. So which scenario should I choose? Okay, so here's how we'll go deep on this. So those of you who've done risk assessments will know that assigning the likelihood scores for different events and indices for some hazards are not all created equally in terms of the climate projections that are available. And there's essentially 3 categories of these. Well, actually, I guess there's 4 categories. The first one let me back myself up here. The first one I'm not mentioning is in some cases, like return periods I've mentioned a few times, you have the luxury, if you have something that's a 1 in 100-year event today, it essentially has a 1% chance of occurring. And you move to, if that becomes a 1 in 20-year event, it's going to a 5% chance of occurring per year. And so you have a nice, clean, probabilistic number that maps right to your 1 to 7 or 1 to 5, whatever your likelihood scale is. And so in those cases, in those rare cases, you have a nice kind of clear-cut answer, work is done for you. But most of your columns in your PIEVC assessments, the hazards, the variables don't map that cleanly. So even things like heat waves, anything with a threshold, anything that cares about heating degree days, anything like that, you can define a heat wave and you can count them. So you can look at, for any given definition of a heat wave, maybe you have 5 days of this particular magnitude heat wave in the past and it goes to 20. So you have a nice clean factor of 4, but that's not exactly a probability. You have to turn that into, okay, so what's the chance of the thing you care about happening? For some variables, it's even further removed than that, in the sense that the variable's not directly related. So flooding is an example of the animation. If you're very lucky, you'll have hydrological modeling readily available for you that, again, uses return periods. And so you have a nice clean mapping to likelihood scores. But in most cases, you might not have flood risk available in terms of return periods, and you might not even have hydrological modeling available. The recording will, just to answer that question in the chat. So yeah, the flooding, not directly available. Oh, yeah, so you might have to use something like, if you don't have a hydrological model, depending on your watershed, maybe you look at, you look at, for some water shortages, you might look at summer temperature. That's driving demand. For flooding, you might look at winter and spring nighttime low temperature if you're in a snow-dominated watershed. And just if you move, if the average temperature, nighttime low temperature moves from one side of freezing to the other, okay, you can assume that you're going from a snow-dominated basin to you have a rain-dominated basin, and that increases the chances of spring flooding. But it's sort of hand wavy. There's an indirectness there, and then you get even some hazards that we really care about are even further removed from that. So the example is air pollution from wildfire. Now, even wildfire is is an example of one of the things that's not directly available, although we're working on it. But it's one thing to have the meteorological conditions associated with wildfire, and then yet another thing to go to, okay, do we actually have forests that will burn in this area? And then, where the air pollution is going to spread depends on so many factors. So you might not have things available at all, even though there still is a climate relationship there. So how do we deal with this? I'm assuming this audience knows this. You've been through this. The reason risk assessments work, despite that fact, is that these likelihood score bins are very wide. So I'm showing here the 1 to 5 scale from the high-level screening guide and sort of the old school original 1 to 7 method A and method B, and you can see in the probabilities in 1 to 7 where if you have 7 bins, then each bin is smaller separation between them. Even in these, there's a factor of 2 at least between each of these bins. So that wide range is what allows us to there's low precision essentially in these buckets is what allows you to to actually be able to come up with answers, even though you have that challenge. So the reason I'm spending so much time on this is just to point out that this is the area where if we can increase our confidence in our likelihood scores or in the precision of a risk assessment, this is the area where there's the most room, not the choice of scenarios. So the combination of this with the fact that the range of uncertainty that comes from scenarios is generally small, except for some variables at the end of the century, means that it's an important question, which scenario should we use? But I just wanted to have all this context that it's not the be all and end all question. It's not like you can't do a risk assessment without the perfect answer to that question, if that makes sense. And so I just have this reminder. I think I've said this in sort of different words already, just that the purpose of the risk assessment in the first place is to surface risks. I wanted to mention this because, the next step after a risk assessment, or maybe even in part of an engineering analysis, is to have a conversation on risk tolerance for design. And I want to distinguish between those two, because when we get to the recommendations, we'll see that, what's the best scenario is different for a risk assessment itself than for the design conversation that happens afterwards. And so before we do that, I have one more PIEVC, and that is which tool is best for building a house. Oh, you know what? I think the PIEVC is probably is not activating here. Okay, so you can put your answers in the chat. Which tool is the best tool for building a house? Keep in mind, we're building a house where we're getting all of our 2x4s delivered in 12-foot lengths. Some of them need to be shorter than that. We do need to hammer some studs together. There's some tile work that needs doing. There's some plumbing that needs doing. Which one of these tools do you pick? Okay, so I'm being facetious. And it's not a perfect analogy to the scenario situation. Maybe a better analogy, which size of wrench do you use? But I'm doing this just to point out, just to prepare you for the answer. Is there's not really a single prescriptive answer that can be given in this situation. Which scenario? Use professional judgment. A lot of PIEVC assessments and risk assessments will have a climate scientist involved. What I can, and it's a little bit awkward because the professional judgment that needs to be used is both climate science and engineering infrastructure. The knowledge of that's relevant to the thing that you're assessing. So it's tricky, but climate services will generally not give a prescriptive answer. Use this one particular scenario because there isn't a one size fits all. There's not a single tool that you use to build a house, and so for the same reason, there's not a single scenario you can use for risk assessment. But I can definitely say that for risk assessment, I've been involved in dozens of them. And the one that's most commonly used, for the last 10 years at least, has been always just the highest one. So that's RCP 8.5 ever since it's been available, and then SSP 8.5 now. It's the one that's most commonly used, and the rationale is that it's engineering conservative. There's now, because it's been in use for so long, an argument that it allows for comparison to other work. I do want to point out, on both sides of this, that you can get an even more conservative option. I have seen risk assessments that want to make sure that they're thinking about the high end of all of that. Those three sources of uncertainty that we looked at. What if the worst climate models, the most pessimistic climate models, I should say, are correct, and what about in the high the more extreme years, yeah, in terms of and in the high scenarios. So I have seen assessments that will take that have recommended using 8.5 and the 90th percentile from across the climate model range of 8.5. So you can go even more sort of pessimistic than using the median result from 8.5. But there are also, I'm kind of using, so in terms of which scenario, Andre, if you were doing a new assessment, if you're going to use 8.5, I would use SSP 5, 8.5. So you just want to use the most recent data that's available. But like I say, if work has recently been done using RCP 8.5, I wouldn't throw that work out. And then, so yeah, on the flip side of being even more cautious is that in some cases, I have seen risk assessments use 4.5 explicitly, or 6.0, although that's not readily available. And 7.0 is, like I said, may be available soon. But again, I want to make a distinction between in the risk assessment itself, and frankly, I personally do find the argument for using the highest available scenario fairly compelling. For the risk assessment itself, you want to flesh out the whole purpose of the risk assessment is to find those potential high risks. And then when you get to the stage of, okay, you're building an actual building. And I'll use an example here that I'm familiar with, a building on campus of UVic. They, at a high level, they considered climate change, but then when they came down to scoping the actual building and the heating and cooling demand for the building, they found that by looking at RCP 8.5 by the end of the century, it would cost literally millions of dollars, which was a sizable chunk of the budget for this building, to design the cooling system to be able to handle the end of the century under it was at the time RCP 8.5. And so they looked at all three for the design. They made a conscious choice to design for 8.5, but the middle of the century. So they did have a larger capacity in the heat exchangers, the hot cold air heat exchangers. They did make some different choices around windows, so it actually impacted design. And they also left. They made some decisions that didn't lock in sort of future retrofit, so it'll be cheaper to retrofit in future. So they looked at all three. You had to pick one to design to, but they considered all three. So there's a difference between looking at this what if scenario under all, how expensive would it be, and then making a sort of risk tolerance cost judgment call when you get to the design. And the important part is that writing that down and stating your assumptions, sort of showing your work, so that when somebody 30 years down the road, there's a retrofit coming along, people know why things were designed to what, and that kind of goes without saying, but it's important to say that state all of your assumptions, show all of your work at every stage. If you're erring on the side of being sort of pessimistic in terms of, or cautious in terms of taking 8.5, you can note that if it turns out that it's very expensive to design to. And last point I want to make that's related to this is that the climate system responds to the total forcing. All it cares about is the number of light bulbs that are at the top of the atmosphere. As I said, with some exceptions, some things care about the relative ratio of some gases to others or whatever. But in general, the climate impacts that we care about in risk assessments are responding to the total amount of forcing. But that's a good thing. It means that you don't have to guess correctly exactly, it's not a crystal ball exercise. Which one of these scenarios is going to happen if I guess wrong? My risk assessment's garbage. That's not the case, because the climate system responds to the total forcing. It's possible to kind of re-examine an assessment if we, if you want to take you want to bring your risk tolerance into it. You can say, well, okay, maybe this 8.5 ended middle of the century. Maybe that doesn't happen by 2050. Maybe that happens by 2070. So you can adjust in your interpretation. if that makes sense. And and so it's a kind of a combination of your risk tolerance and time. How often should a reassessment of risk be done after initial risk? That's a very cool question. I think that'll be a good one for the discussion. So I'm going to give a second to see if Carrie wants to interrupt me with anything before I touch on global warming levels, because it kind of everything we've talked about so far is like walking us right into this thing of global warming levels, which some of you may have heard of. Okay.
Yeah, I think so. There is one question I think could be useful to answer right now, which is just wrapping up your own example that you're using and talking about which scenarios your building project at UVic and actually ended up using. And Andre notes that mechanical systems generally are only good for 20 to 30 years, so the middle of the century. So maybe you're thinking around how you tackled that.
Yeah, so in that one, they basically looked at all three, 2.6, 4.5, and 8.5. Yeah, that's exactly what they thought. So it's important when you think about, okay, mechanical systems are going to get replaced in 30 years, but you can make choices now. You know, if you bake in, not having individual controls in each room, and only having sort of zones in a building, it can be really expensive to put the wiring in later to make that possible. Maybe you put the wiring in now, even though it's only zones, but you have the option to have every room have its own control when you get to hot enough climates that you need to. So it's little things like that you can sort of hedge your bets. That's what was done. So it's not like they've really picked one. For different design elements, they did different things, if that makes sense. So it's like, oh, well, we're sizing the air heat exchangers basically for, I think they took 8.5 2050s. Yeah, they did other components where they sort of hedged the bets. And I think we're rapidly running out of time. So I want to get to the last few slides and leave some time for discussion. So this is kind of taking what we looked at before and flipping it on its head. So here's on the bottom, we have the total greenhouse gas emissions concentration. You could turn this into watts per square meter as well. And you can see the different emission scenarios, or the different SSPs here. This is actually the RCPs, sorry. You can see the different RCPs following the trajectories along these. And while it's true that the higher emission scenarios, they reach, so that, the high emission scenario is the only one that gets this far. It gets here by 2100. There's a little bit of a time dependence between them, but in general, when you're at a given greenhouse gas concentration, it almost doesn't matter. The choice of emission scenario is just going to dictate when you reach that, not not what the temperature change is when you reach it. There's a little bit of so this is the vertical is temperature. There's a little bit of temperature dependence, but not much. And so you can use that to sort of flip this over here and say, okay, so we could design for this level, 1.5 degrees from a recent time period, 2 degrees or 3.5. And now you're not picking a pathway, you're picking a level, and you can invert the question. And the things that I want to say on this, and I'm going to go through this rapidly because it sort of speaks for itself and I want to leave some time for discussion, is that the levels of global warming are a complementary and a convenient way to look at risk. It allows you to assess risk and design for a specific level of warming, but it's not a silver bullet. All three kind of awkward things that we have to deal with are still present. They just move to different places. So the need to choose your risk tolerance remains, but it moves from which scenario to when will a particular global warming level occur. The need to choose multiple scenarios when you get to the design stage remains, but it moves from multiple scenarios to multiple global warming levels. And the uncertainty remains, but it moves from a wide range of projected change to a wide range of when might that level occur. So you're just kind of moving we're moving the interpretation to different places, and it can be a useful way to look at it. And it can also enable, I won't go into the details of what this means, but single model large ensembles, it's what has enabled us to have climate projections for all of the building code projections. These are available at PIEVC has a design value explorer that you can access these now. And these are variables that are usually hard to do. We can't readily do with statistical downscaling. And so for various technical reasons in the weeds, they're able to produce it, but only by levels of global warming rather than by each of the three commonly used scenarios. So I'm going to leave these three questions up as kind of fodder for sparking questions, although I see there are several in the chat already. And
yeah,
I see
thanks
that
so much, Trevor.
ate up all the time.
You did. We've got a couple minutes left. I don't know. I'm so appreciative to Carrie in the chat there. He's been answering questions like crazy. So I'm going to let him weigh in with any like last burning questions. I'm going to suggest we move everything else to the practitioners network after, and we've also got the recordings and everything there. So I'm putting a survey in the chat as well before everybody goes, so they can let us know what they want in the future. And Carrie, I can turn it over to you.
While Carrie's thinking, I'm just going to answer Eric's question there because it's an easy answer. No, I'm not. So global warming levels does not allow probabilities in any. It's independent. So just moving to the global warming level doesn't make it easier to have things available by probability. Anything else, Carrie, that you want to pull out?
Maybe there was a question from Jill Curley at one point, and I just wanted to give you a chance to highlight some of the resources that you'd mentioned before about documented guidance around scenarios that we can point to. They asked specifically for documented guidance on which scenario should be used for risk assessment, but you could use this time to talk about the articles that we have available and whether or not there's guidance around which scenario should be used for risk assessment.
Yeah, no, there is nothing that I'm aware of that's like which scenario to be. This is it. Oh, one thing I should say though, it's not the end of this conversation. This is the start. This is something that I know the PIEVC Practitioners Network and CCCS is interested in further sort of in-depth training, not just like the 1 hour webinar at you kind of thing, but have people break into tables and breakout groups and really like get into the meat of all of this stuff. So expect those. In terms of the learning zone resources, I won't walk through them, but in the slides that you'll get sent to you after this, and that I assume will be posted with the recording as well, there's like a dozen slides or so of useful resources to go both deeper on this stuff, or to, like I said, we kind of started at like 201 with this, so there'll be some sort of basic resources in there as well.
So one other question from Emma around, like this is kind of a more general topic, but Emma has a specific examples that you could use here around, does the weight of scenario choice change depending on the variable that you're looking at? And Emma suggested or asked about sea level rise in particular here.
Yeah, interestingly, sea level rise is probably the best example of a variable where you might want to make a different choice for this scenario than all of other variables. And the reason for that is the sea level rise, especially if you care about the end of the century, has an additional uncertainty that's not really present in other variables, which is, what if big chunks of Greenland or Antarctic ice sheets melt? And so there's sort of an extra high end to the sea level rise projections. There's also, on top of that, there's additional uncertainty in modeling the melt. So the climate models, modeling of melt. And so yeah, on climatedata.ca, for example, where we have the sea level rise projections, there are different, the percentiles that are available there are different than for other variables, and there's an additional it's not a time evolving scenario. It's just at the end of the century, there's a what if, and I don't remember the exact number off the top of my head, but it sort of takes RCP 8.5. These are only available for the RCPs at the moment. The SSPs are coming, but RCP 8.5, 95th percentile, and then add some fixed amount, 85 centimeters or something like that. So yes, the answer is yes, it can matter, although sea level rise is the only example I can think of actually where it does. Generally, everything else, it's better to keep your sources comparable. That said, I mentioned in passing very briefly the design value explorer from PIEVC, and there are some variables that are available there that are really not readily available anywhere else. Things like wind, for example, and personally, if I was involved in a risk assessment, and actually I have since that source of projections has become available, you're better off. You have more information if you combine projections from multiple sources. So for temperature and precipitation, we use the statistically downscaled SSP 5 8.5, and I'm thinking of a recent risk assessment with Transportation Association of Canada. But for some of the other variables that weren't available from there, we used the Design Value Explorer. And in fact, some of the hazards they were interested in, there really wasn't any projections for. I mentioned that category of indirect. So for those, we used the CCCR, Canada in a Changing Climate Report, and that's one of the resources that will be mentioned that'll be included in the long list of resources with the slides, and just use the information there and with expert opinion to come up with how we do that. Okay, thanks.
Great.
It's a plus 65 centimeters. Thanks for posting that.
That's a good transition, Trevor, too. I know you have a meeting to get to. I know others do as well. Thank you so much for your time today. Really, really appreciate it. Carrie, thanks so much joining in. There's clearly a lot of interest and a lot of questions. I hope all of you also join the network and continue the conversation. We'll again include the recordings and all of those resources that Trevor has included. Very last question, because I really like it. In the chat here from Harshan, what climate scientists do you follow to essentially help inform your views and insights? Quickly.
Catherine Hayhoe and Kevin Anderson.
Love it. Easy. Thank you so much, everybody. Thanks for joining us. Get in touch with me and we can put you in touch with Trevor if you have more questions. Follow us and we'll make sure you are aware of future activities. Sorry, somebody says who? Can you repeat that? I heard Catherine Hayhoe.
Catherine Hayhoe and Kevin Anderson. And that's who popped. Simon Donner also closer to home.
Simon Anderson.
Yeah.
Simon Donner. Awesome. Thanks so much. See you later. See you soon. Thanks, everybody.
Thanks.